stuff that I didn't teach you.
That blows my mind.
Needless to say, that was
Get out of here.
a claim. Yeah, that was a claim that I did against the school. I'm not paying for that.
He said that that's people's experience. Okay, do y'all have any homework questions? We've got in 1 week from today, we've got our third exam on chapter 4. Yeah.
1 week from today?
Yep. November 12th, next Tuesday.
12 to whenever. Library. This upcoming Sunday? Yeah. Goal for all of us to have all of us worked out by Sunday. We'll try to do this together if you guys don't already have to listen. Where's going to be your first time?
Okay, this is 4/7's homework number 15. I think we've just barely introduced these types of functions. We did look at one limit that was x to the x, but this ought to be a good. We'll look at a couple more and then be done with 4/7. So evaluate the following limit. Use L'Hopital's rule when it's convenient and applicable. So the first thing we want to do is evaluate the limit directly as x goes to 0 from the right. So I'll just abbreviate here. By direct substitution, we've got 0 to the 0. So that's like the third indeterminate form we looked at. And when you have functions of the form, or limits rather of the form 0 to the 0, 1 to the infinity, and
Infinity to the 0.
infinity to the 0. So any of those three limits means that we have to rewrite the function in terms of e. So we have to rewrite x to the power of 6x as e to the natural log of that thing. And then we always take that a step further and use the power rule for power property for logarithms. So we're going to rewrite it as e to the 6x times the natural log of x. Or e to the power times the log of the base. And compute that limit instead. So remember the limit on an exponential is the same thing as e to that power, but the limit is operating on the power. So that's really what we're computing. I mean, I would write it out like that just because usually the people will compute the limit itself and then just say, you know, like whatever, 2 is the answer. But it's in these situations, it's really e to the 2 as the final answer. So I would write it out like that in full until you're comfortable with getting these. But, you know, then take this limit here and compute it off to the side or down below or whatever. So we'll compute that limit off to the side. And what form does L'Hopital's rule apply to? Directly. What form does the limit have to be?
Infinity over infinity or 0 over 0.
Infinity over infinity or 0 over 0. So again, these things are turned into indeterminate products. As we see here, as x goes to 0, we have 0 times the natural log of 0 from the right, which is, of course, 0 times negative infinity. So we've got our indeterminate product. We need that to be a quotient before we can apply L'Hopital's rule. So how do we turn the product into a quotient? What do we have to do?
Divide
Divide by the reciprocal.
Yeah, divide by the reciprocal. So the natural log we're going to leave alone. We're going to put that over the reciprocal of the other factor, 6x. So we've got ln x over 1 over 6x. So that's just an algebraic step. Reevaluating the limit just to ensure that we are dealing with a form L'Hopital's applies to. We'll have the top approaching negative infinity, direct substitution, and the bottom approaching what? 1 over 6x approaches what?
Infinity.
Infinity. The denominator's getting smaller and smaller, but the quotient gets larger and larger. Okay, so coming from this form, this is where we apply L'Hopital's rule. So we're going to apply that directly to the ln over 1 over 6x. I'm going to just indicate that as such. Limit part is still the same. X is approaching 0 from the right. And then we take the derivative of the numerator, so the derivative of the ln of x, 1 over x, divided by the derivative of 1 over 6x. So what's the derivative of 1 over 6x?
6 over 6x squared.
Because remember, either you have to use the quotient rule on this, or we have to think about it as 6x, that quantity, to the negative 1. Or we can think about it as just 1/6 x to the negative 1, because our 1/6 here is just a constant. So I guess there's a couple of ways to think about it.
6 over 6x squared, isn't it?
Yes, negative 6 over 6x squared. So we'll have a negative 1 over 6x squared.
It's going to be negative. Why is it negative?
Because of the exponent on x, when we take the derivative of that, that negative comes out front, and we subtract 1 from the power. Right, so that derivative here on this thing, we have 1/6 times negative 1 x to the negative 2.
If you use the, oh shit, I can't remember the name of the rule.
Quotient?
Yeah, I'm assuming so, right? The bottom times derivative of the top,
Yeah.
minus, etc. You don't get a negative in that sense, do you?
Well, so we have this here. We have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Whoa, that's way off.
What?
Yeah, no, I know what you mean.
All over 36x
Yeah.
squared. So that's where the negative comes from. So bad.
Oh, that's right.
Try this again. So you get a negative 6 divided by 36.
Yeah, I was switching the numerators,
Yeah.
or the values in the
Oh, these
numerator.
two.
Yeah.
Yeah. Yeah, remember, quotient rule is bottom derivative of the top minus the top derivative of the bottom. All right, so then after we do L'Hopital's, or after we apply L'Hopital's rule, what do we do after that? Yeah, you have to simplify it first. Before you even reevaluate, simplify this, and then just an algebraic step. So we're just going to write equals. And then we've got a 6x squared on top divided by -1 times the 1 over x. So we've got a -6x. And that limit is, we can evaluate that limit, of course. So that limit is 0. But again, that was sort of just a part of the result, right? That limit is for the exponent up here on e. So our final result needs to be e to that power, which e to the 0 gives us 1. So that's the final result for that limit. Anyone have any questions? All right. Any other questions on the homework?
That was x to the 6x, right?
Right. This is our function here. Is our function actually defined there? At 0, 1? Oops, I think that's going on. So it's the same function, written out exponentially. It's not defined at 0 because the natural log isn't defined at 0. So we have a hole there at 0, 1. As x approaches 0, y approaches 1. So no more homework questions? Okay then. Yeah, and so the one we looked at last class was x to the x. We'll look at a few more of these. So let's compute limit at infinity, 1 plus 1 over x to the x. What is limits at infinity? What do they tell us? And behavior. And typically that just translates to whether the function has a horizontal asymptote. Okay, so directly substituting as x approaches infinity, what do we get?
We get 1 to the power of infinity.
1 to the power of infinity. Do y'all agree? The 1 over x as x approaches infinity is approaching 0. Okay, so 1 to the infinity. Again, another situation where we have to rewrite the given expression or function as e to the x natural log 1 plus 1 over x. And then so we're computing e to the limit at infinity on x natural log 1 plus 1 over x. So we'll do that off to the side as well. I mean, if we've seen in the general sense that you're always going to have to rewrite this limit as well, because that limit, when you rewrite it as e to that power, will always be an indeterminate product. But we'll go ahead and check and verify. As x approaches infinity, we've got infinity times the natural log of 1, which is 0. So there's again our indeterminate product. We want to leave the natural log alone and reciprocate the x, the factor of x here. So just an algebraic step to rewrite our product as a quotient. So we have the ln of that quantity divided by 1 over x. Those two steps of rewriting it as e to that power and then rewriting it as a quotient for those 0 to the 0, etc., those three, they always equate to something like this. You have to rewrite it in terms of e, and then you have to turn the product into a quotient. And we'll verify again via direct substitution that this is actually of the form we can apply L'Hopital's rule to. So we have the top, the numerator turns into the natural log of 1 as x approaches infinity, ln of 1 over, as x approaches infinity on the bottom, 1 over a large number gets smaller and smaller. And of course ln of 1 is 0, so this is something that we apply L'Hopital's rule to. Excuse me. Okay. So then, well, perhaps we can compute these derivatives below, but we've got to take the derivative of the top. Derivative of the bottom shouldn't be that big of a issue. But what's the derivative of the natural log of 1 plus 1 over x? You do that here. So that's a chain rule. Outer function is the natural log. So we have 1 over, the derivative of that is 1 over the argument times the derivative of the argument. So we have 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x. And what's the derivative of 1 plus 1 over x? Yeah, negative 1 over x squared. So let's just combine those because we see this negative 1 over x squared. If we multiply that through the bottom, it'll get rid of that sort of complex fraction. So we have that derivative as negative 1 over x squared plus x. Well, actually, so we could write it like that, but actually I think it's preferable to leave it as the previous step.
Yes.
Because we have to put this derivative here. So if we put this derivative here, it simplifies a little bit easier. Right? As opposed to just multiplying through.
What if you combined it?
Yeah, if you,
Combine it, but don't distribute. Just say -1 over x, and then put the 1 over 1 plus 1 over x in parentheses with that. Is that still going to make it a little too?
I would have to say, so say it again, what would it look, what would you
Just
write it as?
-1 over x, parentheses, 1 plus 1 over x.
After you've simplified all of this, or just the derivative here?
Just the, oh, you're, okay, never mind. I misunderstood what you were saying before. You're good.
Okay.
Scratch that, scratch all that, you're good.
Yeah, I mean, if you simplify the derivative like this, and then you would have to simplify that, so you would just have that negative, canceling this negative here, and the x squared. So you would have this right here. You'd have a positive once we put it back into our original limit, and then you would, at that point, you would have to factor one of those x's out to simplify that. So I don't think it's detrimental to simplify the derivative first and then put it into our limit. But here, it's easier to see that these two things divide out. So that's L'Hopital's rule. And then simplifying that gives us the limit as x approaches infinity. Just of our little quantity here, 1 over 1 plus 1 over x. So as x approaches infinity, that limit is 1. We'll use this column. So this is kind of this. Okay, so remember that's not the actual limit because that was just the power attached to e. So the answer is e to the first, or e. So that limit is 1. I mean,
Wait,
e.
what?
e to the first. I wrote the wrong thing.
E to the first.
E to the
I
first.
was like, I don't know how that from 1 to 0.
Yeah, that was.
I'm not gonna question.
Yeah, I don't know where I got that
You
either.
just randomly subtract 1.
E to the first is e. All right. So you might have actually seen e defined that way. I think some like algebra and pre-calc books will even say e is this number 2.71828 ... but it's also equivalently defined by this limit. So now we can actually see how that actually works. Because before L'Hopital's and before limits, you just look at that and say, all right, well, I guess that's e, I don't know. We can show that for sure that this limit is e. And it also kind of goes back to, when you, like in algebra or pre-calc class where you looked at this interest formula. Do y'all remember that? And then it said, like, if we compound continuously, then what we get is a equals p times e to the power of RT. Does that vaguely seem familiar? Well, compounding continuously means you're compounding all the time, which means when you compound continuously, the number of compounding periods approach infinity. So we can kind of see that we've got, although we didn't look directly at 1 plus r over n to the power of nt, this, if we compute the limit at infinity on this thing right here, this piece right here approaches e to the RT. So that's where that comes from. Very similar. I mean, you've got a couple more numbers or variables, letters floating around, but we could do this, compute this limit just like we computed the previous limit. So anyhow, do y'all have any questions at this point?
What did we say the final answer was?
It was E. Yeah. Which again, since we're computing a limit at infinity, when we graph this function here, 1 plus 1 over x to the x, it'll have a horizontal asymptote at y equals E. Do that with, no, whatever. So there's our y equals to e, and that, we see that function approaching at infinity. Of course, we're looking at this function instead, but what's this? We can see they're the same function. All right, I think this is our last example. No, I'll delete this page. Two more. I do want to mention this problem here that's from your homework, and then I'll have y'all attempt number 4. But the function here, the root ax plus b over root cx plus d, where a, b, c, and d are positive real numbers, they want you to show L'Hopital's rule fails for the limit, and then compute the limit using another method. So we had, I think we saw 2 instances where L'Hopital's rule failed, in the sense that we just kept getting an indeterminate form. Like it never resolved into something we could actually compute. So when you compute this limit directly, we've got an infinity, direct substitution, the square root of an infinity over the square root of another infinity. So it's not that L'Hopital's rule fails to apply to this particular limit, because it does. The limit is of the form infinity over infinity.
But it just doesn't help us.
Yeah, right. So when we're going to compute the limit at infinity for root ax plus b over root cx plus d, using L'Hopital's rule, we're going to take the derivative of the top with respect to x. So what is the derivative? What is the derivative of the square root of ax plus b with respect to x?
ax plus b over 2, or ax plus b squared.
So then we want to think about that perhaps as the derivative of the quantity ax plus b to the power of 1/2.
Oh yeah, that's right. I forgot the exponent.
We'll keep this stuff off to the side. So we have 1/2 times ax plus b to the negative 1/2 times the derivative of the inside function, so times the derivative of ax plus b, which is just a. Derivative of ax is a, the derivative of b is 0. So yeah, you could say it's a over 2. So we could say that's, we'll write it here. So that's the derivative of the numerator. And you've got a similar situation for the bottom. Derivative of the denominator. Let's do c over 2 times the square root of cx plus d. So that's L'Hopital's rule, derivative of the numerator divided by the derivative of the denominator. Then we simplify the result. So let's simplify this thing here. Okay, the 2's will divide out, right? We've got two of these roots up top, c on bottom. The 2's divide away. What are we left with?
A square root of cx plus d over c square root of ax plus d. Or we pretty much just flip them.
Yeah. Do you all agree? Okay, so L'Hopital's rule, we simplify, and then after we simplify, we reevaluate the limit. Reevaluating that limit gives us what? Still infinity over infinity. So in fact, you'll just keep, even though you'll get higher roots, like cube roots next, they'll end up flipping again. So like the cube root of ax plus b, once we apply L'Hopital's rule again, and again and again. The point of this, your homework actually has you compute L'Hopital's rule again after this. But the point is that you always end up with a root of some kind of cx plus d over ax plus b, or vice versa. So this is, let's just write here, by direct substitution, it's infinity over infinity. So all of these L'Hopital's rule, you can apply it 10 different times, you're still going to have a limit that's infinity over infinity. And that's, I guess in a sense, why it fails. It's not that it fails, it just doesn't produce any results. Does anyone have any questions about that? So with that in mind, then it says, that's pretty much showing L'Hopital's rule fails because the limit is always infinity over infinity. And then it says, find the limit using another method. So what's another method we could use to compute that limit? Do what? So like if we squared this whole thing, we wouldn't be dealing with the function itself, right? You have a completely different, like if this was f of x and we squared it, now we're computing the limit on f of x squared. Which I guess you could, but then to answer what the limit is on f, you would just have to take the square root of your result. So we don't usually do that, so I don't want to do that now.
Do you multiply by reciprocal?
And what do you mean? Like what would we multiply by?
Or no, not a reciprocal, a conjugate.
Conjugate? Okay. What would the conjugate look like?
Root ax minus b? I don't know quite where I'm going with that.
Yeah, it's fine. We can always see what it yields. Like that?
Yeah.
Okay. So that'll definitely get rid of the root up top. So we just have ax plus b up top. On the bottom we have two of roots multiplied by one another, so what could we do there? They wouldn't cancel out because each root is not being squared, right? So let's just write this here. We would have this
Probably just
times this. Is there anything we can do with that? Still infinity over infinity. If you can figure out what to do here on the bottom, then you can kind of resolve the issue of the original limit. So although I can't cancel those radicals, what could I do with those if cx plus d and ax plus v are real numbers? How about this? How about if I ask you what's the square root of capital A times capital B? How could we rewrite the square root of A times B?
Square root of A times square root.
Yeah. Square root of A times the square root of B. Is that right? So this is kind of what we're dealing with on the bottom. We could rewrite it as a product under a single root. But I don't, like, even at that point, I don't think it's necessary because the square root of A over B is also the square root of A over the square root of B. So I don't know that there's anything wrong with this thing here, but I don't think it's necessary. Because at some point you've got to combine the expressions under the radicals. So we might as well just do that from the very beginning. So just rewrite this limit as x goes to infinity. Of the square root of ax plus b over cx plus d. And what can we do from there? Does the limit operate on the square root part? The x's wouldn't just cross out, but the limit doesn't affect the square root, right? The square root is there regardless. The limit is operating on the ax plus b over cx plus d. Does everyone agree with that? Remember, as long as that function's continuous at x, then we can pass that limit through the radical. And so how do we compute the limit under the radical? What kind of function is that? Ax plus b over cx plus d. Rational. We got a polynomial over a polynomial. How do we compute the limit at infinity on a polynomial?
We take the reverse to the over z.
Yeah. right? We have a degree 1 divided by a degree 1 polynomial. And in other words, we look at just the leading term divided by the leading term. Since x is going to infinity, that's the same thing as computing the limit at infinity on just ax over cx. Yeah, so now we can cross out the x's, but we couldn't with the b and the d. Since we are going to infinity, I guess we could say that at this point. So it's the square root of a over c, or the square root of a over the square root of c. So that's what that limit is. And again, that's kind of just showing you that, you know, just because you have an indeterminate form that L'Hopital's applies to, it's not always the case that it's going to solve the problem for you. And also indeterminate, like a infinity over infinity or 0 over 0, can be any value. So here the value is root a over root c. All right, any questions or comments about that question? All right then. So y'all try this limit number example 4.
So this is where you have to use B, right?
Yes.
Like how do you
So,
convert it?
so far, this is how I would do it. So when you try to do just service, and then change it so you got your taxes. So what it's going to do is tan out natural logs of sine x. So then you get your 0 times infinity.
I thought it had to be 0 over 0.
Well, yeah, but now we have to get it there. Since we have a natural log, we'll on top of the touch.
And L'Hopital's rule for the limit of x equals 0 on ln sine x change x or
No, you don't need to look on the
Oh, over 10 is just 10.
Yes. That's
Why do you know what you're doing? You haven't even been here. You haven't even gone here.
So that will equal with direct substitution.
Yeah, but it doesn't give you a lot.
After here, I get it.
Yeah, but they were like 0.
Here.
See example 1.
It doesn't matter what sign it is.
It's just
still,
negative, yeah.
It's some infinity or some infinity. Now you can look at this.
I don't know what element sign it is.
So, but remember though, that L'Hopital's rule doesn't apply.
Then you have 1 over sin
So over to the side becomes
tangent x.
the limit. Oh, okay.
There's a lot.
I see.
So you have, so
That's just the same.
How does Where did this denominator
like remember this, like if I have one function times another.
So why is this
Oh, you're
divided?
saying you have this divided? I'm sorry.
That's what I got stuck on. I asked
Oh, so you're saying multiply g times
How did we go from this?
So, well, it's actually, this is g
Not the
over
numerator, but how did we
this,
go from
but
having
it's actually
just
times.
a, like,
So I wanted to add this form here.
yeah.
So you could have it the other way around?
That's, yeah, you could have it as f over
And we have to get it to a form
It's just
of
easier to get on a
0.
specific type of problem.
Yeah,
That
So
way.
instead of
because
multiplying the natural log of this times that, we can divide the natural log by the reciprocal of that, which winds up giving us one of the indeterminate forms, which would apply.
But not the negative.
Which would apply. Does that
So
make sense?
then, on this example, how would we
that way, and then
make
divide
it?
it.
So you do the same thing.
This is the natural log of this thing right
And
And
then
you
you
just
multiply it by the reciprocal.
By 1 over tangent x?
Yep.
Oh,
Which that,
okay.
1 over tangent x,
So those derivatives will be able
the
to.
natural log of sin x over tangent x. It makes the derivative.
This is what I'm attacking.
Yeah. This is the net limit as x goes to 0.
Yeah.
You have to have a natural log of
Okay.
So before you simplify this though, so now you just, yeah, you have
And then you take the derivative.
You chain the top.
Yeah, so I'm doing the derivative.
just to make it take
Rewrite that.
And then just take cosine
For the closure, yeah.
Right.
Kind of way.
So you would either have to do
The
the
numerator. And you have to. Okay.
You couldn't, that bottom function is a quotient. So you couldn't just take the derivative.
Is it,
So it's just, Like you gotta take the derivative of just the top and
It's
bottom.
a chain rule.
For L'Hopital's rule. So like it's L'Hopital's rule is for limits like that.
So that works.
But
Is
they're
the LHS
equal to these two things, or this thing rather.
What's the derivative of cosine x?
But your function on top is, that's the element of sine.
But can't you figure that out
Take
by
that
using
derivative,
chain
there's
and then the
another-
function is already.
Then you have to do and cosine.
So you gotta take the derivative.
Because to nail it, then you have to do.
which you would have found out by doing chain rule. When in doubt, do chain rule. Chain rule works for literally everything.
Literally everything.
Literally add a negative. I redid the
Cosine
So
over
that'd be
sine.
cosine over sine.
yes, yeah, I realized that. We're in the right.
And cosine over sine? What is cosine over sine?
Yeah, top is in
So it's just cotangent over cosine?
Tangent over negative cosecant squared. Because you have to take
The derivative.
the derivative of cosine. Just wait. Now we have to plug it back in. We do eventually have to plug it back in.
But what do we do? Cosine of x, cosine of 0.
As they approach 0 is.
Oh, yeah, right.
Yeah, and it's from the right, yes.
Yes. So it's infinity over infinity?
Is it one getting infinity or negative? Yes, you do have to apply Logarithms.
Oh, yeah.
You don't have your note cards. What kind of foolishness travel without their note
Okay. Okay, we've got
There's no problem.
No, I'm saying you rewrite. So like we have to take the derivative of x and 1 over t.
two cotangent.
X is the same thing as
Well, because then you take this and you plug it in to e.
no, you just rewrite it. Because otherwise you have to.
This no one's different. We're at this.
Yeah.
So then,
It's like, so we get.
so we apply
Infinity times.
and then we plug zero in.
Well, yeah.
Plug zero in.
Just get rid of the 1 over
It seems to make sense. I don't have a calculator on my calculator.
I don't think the trouble is just
take the derivative oh wait, no, you have to take, so after you rewrite, then
So then you take the derivative.
negative
The derivative.
I'm just happy I didn't get any of
How do you calculate that? I mean, it doesn't.
I don't know.
Because there were different elements.
Okay. So I feel like this is not the best method.
I feel like
Well, that's not true.
No,
That doesn't work.
that being the case, like, we apply.
It just means we have to do it again. Well, it's just like that this is not.
That's part, that's, the bottom here is the derivative.
I totally didn't even notice.
Oh, yeah, so cosine over sine, so that would be.
So I've decided I don't like it.
Yeah, it doesn't work.
So that's why I think like.
Whatever, I'll just trust you.
I told Toby, I was like, we're gonna need your starting discount.
Then you can cancel out the cosecant, right? No. Yes, you can.
Some of these people are from Toby's, it's not just my responsibility. We just are really popular and have a lot of friends, and it's stressful.
Yeah, me and my friends like stopped.
That's still one of, I don't think this is possible.
No, it's
Now it's
one
cotangent.
over.
All of my friends are from work, so we know we have to be.
Yeah.
Undefined.
No. You're not gonna.
Well, we use top twelve rule again.
So, 1 over.
Toby's not trying to sell me on
It's 1 divided over, 1 divided by infinity is 0.
Oh, wait, because that's a negative, because it's obvious.
So this is just tangent, right?
Well,
Yeah, that's what I saw.
Or digits.
this would be cotangent
There was
x over
this thing
2,
that said,
right?
you spend my time off request really short staffed related to you. And then someone said, you either show up for your shift or you get fired.
This is the exact same thing.
But after the schedule was already being finished or worked on, we would have probably approved it if it would have told us like a week ago.
Okay. Yeah, it's the exact same thing. Yeah, and we get that. I don't know. Yeah, which we get there. So we end up with 1, negative 1 over 2 cotangent x.
Yes.
Okay.
Yes.
Carry my negative.
Super good.
Carry your negative.
I didn't. We're just confirming. But I like believe in you.
I appreciate confirmation bias.
Yes. You can't. You're left with negative. Yes, so we negative 1 over how do you calculate if it's positive or negative? You either plug in values that are really, really close to 0 or
So what did you negative 1 over sine?
negative 1 over infinity plus 0. Because then we've already got
Where are we approaching from the right? 0.020.
So that means it's 0.
Yeah, it's positive infinity.
So it's 1 over.
Positive 0.
I'm so glad I figured this out.
Yeah, good job.
It's just 0.
Well, okay, so that would make it dividing by.
And that's not even all of it.
No matter what you do.
And now you put that.
In the kitchen, I'll be like, it hurts. It'll be like, why? And I'm like, I'm carrying this
I am
restaurant.
going to main.
Good job.
I have a lot of mess down here on this. Everything up here is important.
Okay. Yeah.
Everywhere.
Okay, cool. That's fine.
There's not a single place that I'm.
That's totally fine. So show me how to figure out.
Getting to calculate the
We
derivative.
started with this situation. And then we got lost. It was just, I think that the main issue with this problem, I say that I got lost.
Right.
of how to compute signs that aren't
Yes, okay.
calculated.
So, if you wanted to, you could just get 1 divided by,
Because that is no
secant, it's 1 over sine.
That makes it a little bit easier to solve that as a constant times.
Yes.
Come out to
1 over sine of 0.0001.
over negative
Because then it'll give you, or
which is the same as cosine x over sine x divided by negative 1 over sine
because, yeah, if you try to divide by 0, it's like, no, you're about to
Cosine x.
Right.
Oh, so you're saying
Right.
flip that back?
No, I'm saying to simplify this. What's cotangent?
I can't say.
Right, what's cosecant? Right, and then write it like that. Put it into a single fraction, that's what you get. You factor out sine. Sines cancel out, and cosine times sine, and then evaluate it.
So you're saying from this point here, don't try to simplify it that or that way.
Leave the numerator
as
leave the numerator as you have
I feel like
it.
I'm
Simplify
million
it
of
to
those
cosecant squared x.
I think it was like,
Because that's negative 1 over
the only
sine
reason
x.
it took so long for them to sell out is because of the website. I heard
Because
that
you
like
have
other
everything right,
websites that
you know what I
Shopify
mean, you're just leaving it.
supports were down to
overly complex.
like Shopify versions. Yeah, because I was hearing other people being like, yeah, I was trying to buy from another website that's supported by Shopify.
Found it, got it. So then, wouldn't that be negative?
Yes.
Yes, because it's negative cosecant squared.
That was telling them.
Wait,
It's the same answer.
It's the same answer.
Because then you just get a negative.
Who's like,
Yeah, you get a negative 0.
It's negative 1 over sine squared x.
Negative.
Because cosecant squared is supposed to be 1 over sine x times 1 over sine x.
All right, I think everybody was okay up to maybe these 2 steps here. Please remember to, if you're using L'Hopital's rule, it applies in the sense of a limit. So like, you know, if I'm writing like this thing, and then I write like this, it's, I know you know what you're doing in your head, but it doesn't make any sense to write that stuff out. So first of all, you need a limit in here, and second of all, you need to indicate when you're using L'Hopital's rule. And the limit has to be here too. Otherwise, it's not, I don't know what the word is, but it's not appropriate. I mean, I know you know what you're doing. Okay, so we have a product tangent ln sine. We can't just take the derivative of that because it's an indeterminate product, and L'Hopital's rule again is only applicable to quotients 0 over 0 or infinity over infinity. So then we have to rewrite the product dividing by one of the factor's reciprocals. Once we have it in this form that L'Hopital's applies to, then we have to apply it directly to the function that gave us that form. Okay. And what I would do from here before I actually applied L'Hopital's rule is I would rewrite this limit once more. Various people did various things, but I think if we rewrite 1 over tangent as just cotangent, it might be a little bit easier to simplify. I saw a couple of people do L'Hopital's rule twice. Really, you should only have to do L'Hopital's rule once. So it didn't throw anyone off, but really in practice, if you're applying L'Hopital's rule to something else that it doesn't apply to, it can totally lead to erroneous results. So if you applied L'Hopital's rule twice, you shouldn't have, and you just got lucky. Okay, so then now we're going to apply this rule. So we're going to when I take the derivative of the top and the derivative of the bottom, I'm going to indicate that And again, L'Hopital's is just the derivative of the top over the derivative of the bottom. It's not a quotient rule. We're not taking the derivative of that entire function. So derivative of ln sine, 1 over the argument times the derivative of the argument. Okay, so we have cosine over sine. And then the derivative of cotangent is negative cosecant squared. So L'Hopital's rule, then we simplify. As far as trig functions are concerned, the simplification, I think that's generally the best approach, is to write everything in terms of sines and cosines. So we have to simplify this. Same limit. Oops. We're going to just rewrite the denominator as negative 1 over sine squared, and then invert and multiply. I know it's a pain to rewrite the limit over and over and over again, but you kind of have to do it. I mean, if we're going to say, all right, now I'm going to simplify this thing, I could take this off to the side and just simplify that, and then put it back here at this step, once I've completed simplifying all of that. But if you're computing limits and using L'Hopital's rule, those things need to be clearly indicated. Otherwise, the things that you're saying are equal, really aren't equal. So we have a negative sine squared cosine over sine. So that's just going to simplify to negative cosine times sine. So there's L'Hopital's rule. We've simplified. Now that we've simplified, we reevaluate this limit. And when we reevaluate, we get 0. So are there any questions on this? The limit is for the power on E. So that's 1. It's not always the case. It was, one of the questions was, or something that was brought up was, if I have e to the power of 0 times infinity, or if it's e to the power of 0 times negative infinity, isn't 0 times a number always 0? So won't this always be e to the 0? And the answer, in short, is no, because all this means in the context of a limit is that this factor is getting smaller and smaller, but this factor is getting larger and larger. So it's not that we're multiplying a 0 times an infinitely large number. It's smaller and smaller numbers times larger and larger numbers. And it really depends on which one of these approaches the quickest. So if this thing's getting super small really quickly, then yeah, it will be 0. But we're not going to talk about growth rates or anything. But it depends on how fast these things are approaching their respective limits. So it's not always equal to 0. So it's not always e to the 0, which is 1. I know a lot of examples that we've had do end up being 1 as the final result, but not all of them are. Okay, so are there any other questions about this problem? All right, so there's our function. We're approaching 0 from the right. We're coming this way. We know that's actually a hole there. Yeah, because of the natural log. Maybe it doesn't like that here. Yeah, so we see that function's the same. Turn that off. So 0 undefined. I'm not quite sure what this software is using to graph this function. To have it tell us that there's a definite point at 0, 1 there. This is what we're looking at. 0, 1. There we go. All right. If there aren't any questions, then we'll take a break and start 4.9.
It's interesting.
Interesting.
Gonna confuse the crap out of me. I don't know why half of it. Yeah, 5 minutes.
It was those are all and then I did the knowledge check. I can show you.
I was like, put that back outside.
Okay, so in 4.9, we're talking about the reverse process of finding derivatives, antiderivatives. Antiderivatives do lead us into Chapter 5, and Chapter 5 is, so really the antiderivative piece is like the other pillar of calculus. It sort of develops into the other pillar. So primarily Calc 1, the rest of Calc 1, we focus on antiderivatives and what they actually do for us. And then if you do go on to Calc 2 is all about antiderivatives for the most part. So in Chapter 3, when we said, hey, here's a function, what's the function's derivative? Depending on what the function was, we had different rules to find the derivative. When we talk about antiderivatives, we're given a function, lowercase f, and we want to find a function whose derivative is the function that's given to us. And capital F is what we're going to call the antiderivative. So for example, if it says find the antiderivative of 2x, what we're thinking about is, okay, what function did I take the derivative of in order to get 2x? Yeah, x squared. So that's how we're, so this is to find the antiderivative of this. Antiderivative of f is the function we take the derivative of in order to get 2x. So that has to be, we'll see this, we'll modify this in a little bit, but if we say that the antiderivative of 2x is x squared, because the derivative of x squared is 2x.
But couldn't it be like 2x plus 2 or 2x minus 3?
Right, yeah. So antiderivatives aren't unique because we know, like, let's just look at this. We can check our antiderivative, check. So since the derivative of capital F is the original function, we know for sure that x squared is an antiderivative of 2x. Does that make sense? Does anyone have any questions about that? At the very basic level, that's all an antiderivative is.
What does the antiderivative tell us?
Like, what does it do for us?
Yeah.
We'll talk about that in chapter 5. It does a lot of, there's a lot of applications to it. Like it can tell us force, work, it can give us volume, give us area. It really depends. We're just going to tie it to one thing specifically in chapter 5. But yeah. But also, if I said that another antiderivative of 2x would be, I don't know, x squared plus 5. That's also correct, because if I take the derivative of x squared plus 5, I still get just 2x. Because the derivative of any constant is 0. So we'll kind of state that in a moment, but really antiderivatives aren't unique. You can have infinitely many antiderivatives given a particular function. But that's the idea of an antiderivative. What function do we take the derivative of in order to get the function that's given to us? So find the antiderivative of the following. F of x equals 1. What's the antiderivative? And we'll just, since the textbook denotes antiderivative as capital F, so will we. So what's the antiderivative of 1? X. Yeah, we'll add the plus numbers in a minute, but we just want to get the idea of antiderivatives, because we're used to working with derivatives. Now we just have to kind of think in reverse.
So are we almost treating f of x as f prime?
No, it's not. I guess.
Sense.
Yeah, in a sense, you
like
could think of that.
when you look at it as
Yeah.
this capital F of x in relation to
Mhm.
f of x, you're almost thinking of f of x as f prime of x.
Yeah. So
and then you're finding the reverse.
the reverse, right? So we could say, okay, here's the derivative is 1. What's the original function?
Right.
Yeah.
Okay.
What's the antiderivative of cosine x? Sine, because the derivative of the function sine is cosine. And we'll write. I'll just write this for a couple of these. So the antiderivative of 1 is x, since the derivative of x is equal to 1. Or the function we started with. The antiderivative of cosine is sine, because the derivative of sine is equal to cosine. What's the antiderivative of sine? Negative cosine. Antiderivative of sine is negative cosine. Since the derivative of negative cosine is sine. Okay, what's the antiderivative of 1 over 2 times the square root of x?
Square root of x.
Square root of x. So the function we take the derivative of in order to get 1 over 2 root x is root x. How about antiderivative of 1 over 1 plus x squared. Derivative of tangent is inverse tangent, yeah, inverse tangent. The derivative of inverse tangent is 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared is inverse tangent. All right, any questions on antiderivative stuff? And thinking about the derivatives in reverse. Well, so let's just mention this here, that as has been pointed out, the antiderivative isn't unique because the derivative of a constant is 0. So all of these that we looked at, it's a technical thing, but all of these functions that we're describing here as the antiderivatives, really we could have plus any constant in there and it would still be an antiderivative. And in fact, inverse tangent of x plus some constant is the official antiderivative of this, because that gives us all of the antiderivatives. If we just looked at when c is 0, we have just one specific antiderivative. So, you know, all of these really need to be that function that we determined plus some constant. So when you find an antiderivative, you'll always have a plus c. So it's, you know, this derivative, antiderivative is sine x plus c. This should really be x plus c. And I think, you know, that's a minor thing that's often overlooked. The main thing is being able to find the antiderivative. So this, we should modify some of these, but because any constant we have there, the derivative is still 1. Any constant we have here, the derivative is still cosine, and so forth. Is everybody all right with that idea? I usually won't take points off if you forget plus c, but you should remember the plus c. If any of you are going on to higher math, eventually the constants start to matter. Okay, so I'm just going to put the definition from the textbook in here, and then the idea of the plus c as well. So the definition of an antiderivative is a function, capital F, is an antiderivative of whatever function we're given, provided that the derivative of capital F is f of x. So in other words, and we'll talk about this a little more in detail, but in other words, this piece right here, that's saying the derivative of the antiderivative. The derivative of the antiderivative is a given function, just like the square root of x squared is x. Is f of x. So we'll talk about this in a little bit, but it's saying that they're inverse operations of one another. If I take the derivative of a function and then the antiderivative, then I'm back at that function. Or if I take the antiderivative and then the derivative, I'm back at the function I started with. So as discussed, we're really looking for the family of antiderivatives, capital F plus C. And what that'll give us, like visually, if you remember, like if you have a graph and you just add or subtract numbers to it, all it does is move your graph up and down. So you really have all of them, all of those graphs. All of these things in blue are antiderivatives. Instead of describing all of them, which we can't, we just put plus C. So like, you know, that G of X or that capital F of X in black here, that was, you know, our original result, but then we went and added the plus C to all of them. So that's what they mean by a family of antiderivatives. Okay. Do y'all have any questions on any of this?
As far as the exam is concerned, is the capital F adequate notation, or are you going to have any additional notation on derivatives?
Yeah, so we're going to actually change up the notation a little bit. It's more conducive to what we see in the future. So the way we're going to note the instructions to find the antiderivative of f of x is the following. We're going to have this elongated s with our function here, and then we're going to have next to that a dx. And that dx, we'll see, I guess we'll see a little bit more in chapter 5 what that actually is. But for now, we're going to read this symbol as find the antiderivative of f of x with respect to x. And that with respect to x part is coming from this piece right here, this dx, that tells you with respect to what variable do we find the antiderivative. Just like when we wrote the derivative of a function, we had the derivative with respect to x. That's what that dx in our antiderivative notation means. So that's the notation. Instructions could be evaluate or find the following. One, let's look at the antiderivative of 4x cubed dx. So all that means is find the antiderivative of 4x cubed, right? In other words, what function do we take the derivative of to get 4x cubed? Yeah, x to the 4th plus c. Finding the function is the hard part. Adding a plus c at the end is the easy part. So the thing with derivatives is that it might not have been terribly easy to take a derivative depending on the function, but you always had a specific set of rules that said if you have this kind of function, then this is how you take the derivative of it. The antiderivatives are much more difficult to compute, but when you compute an antiderivative, you can always check your work. Did I take the antiderivative correctly? So we're going to check, does the derivative of the antiderivative actually equal to the function that we were given? So is that equal to 4x to the 3rd? So even though antiderivatives, as we'll see, are harder to find, they're easier to check. When you found a derivative, there really wasn't any check. It's just like, well, I hope I did that rule correctly, right? The process of finding the antiderivative is much more difficult, but we can actually check your work. So that's the compensation we, I guess, gain and lose. And of course, we know for sure that the derivative of x to the fourth plus c is 4x cubed. Okay, a few more of these. So the antiderivative of -1 over x squared. So in other words, what function do we take the derivative of to get -1 over x squared? 1 over, sorry, say that again? 1 over x, what do y'all think? Derivative of 1 over x is -1 over x squared. So don't forget your plus c. There are rules that we look at to compute antiderivatives. We basically only get 1 in this section, and then 1 in chapter 5.5. The other rules for finding antiderivatives would be seen in Calc 2 if you take Calc 2. So there's really only 2 major rules that we learn for antiderivatives. Everything else is based on our knowledge of derivatives. So what's the antiderivative of e to the x? E to the x, right? Because the derivative of e to the x is e to the x.
And is there going to be like a method of doing this, or like, does it say?
Yeah.
Okay, I assume so. Just like
Yeah.
we're supposed to like guess and like hope that we figured out.
Right now, a lot of these things are just based on knowing their derivatives.
Yeah.
Yeah. We only get 2 methods in Calc 1 for finding antiderivatives. And you know, even in Calc 2, if you see this, find the antiderivative of 1 over 1 plus x squared. Even when you learn a method to find the antiderivative, it's much more of a lengthy process than just knowing, oh, hey, that's inverse tangent. Like if you know that's inverse tangent, you probably save yourself 5 minutes at least of work to actually come up with a method to find that is the answer. This 1 over 1 plus x squared as the inverse tangent, that's a really, really common function, and so is the antiderivative of 1 over the square root of 1 minus x squared. So what function do we take the derivative of to get 1 over square root of 1 minus x squared?
Inverse sine.
Yeah, inverse sine. So the antiderivative of 1 over root 1 minus x squared is inverse sine. Yep, plus c. So those are 4 and 5 are 2 really, really common antiderivatives. What about the antiderivative of secant squared with respect to x? Tangent, yeah, the derivative of tangent is secant squared. How about the antiderivative of 4 times cosine 4x? Close, not quite. Yeah, what do y'all think? Sine 4x? Yeah? So we can check if we're not sure, check. What's the derivative of the sine 4x, of sine 4x? Yeah, derivative of sine is cosine times the derivative of the argument for cosine 4x. About the antiderivative of 3e to the 3x. Yeah. The derivative of e to the 3x is 3e to the 3x. So the antiderivative of 3e to the 3x
Plus c.
is e to the 3x plus c. So you could see how these things could get really complicated, right? When we look at derivatives, especially that involve like products, quotients, and chain rules, a lot of things that you look at, it is not obvious at all what function you take the derivative of to get the antiderivative. So even these, even these simpler ones that involved a chain rule, we will develop a technique for those as we move through chapter 5. What about the antiderivative of 1 over x? Good, yeah. The derivative of the natural log of x is 1 over x. And it's actually, we didn't really go into a lot of detail, but the derivative of the natural log of the absolute value of x is still 1 over x. So we're going to say that the antiderivative of 1 over x is the natural log of the absolute value of x. And that way we have more agreement on the domain of each one of those. So like the function 1 over x isn't defined at 0. ln of x wouldn't be defined for negative numbers and 0, but if we take the ln of the absolute value of x, it's also undefined only at 0. Okay, do y'all have any questions at this point? Oh, we did these. So finding an antiderivative from a known derivative formula, or from a known derivative, is based on the fact that the derivative and antiderivative are inverses. And so more or less we get kind of two things, right? Because the square root of x squared is x, but the square root of x squared is also x. So you always have that like two-way representation for inverses. So if I say the antiderivative of this function, but then I take the derivative of this, and maybe we'll refine this later in chapter 5, but the derivative of an antiderivative would simply give us the function that we started with here. Also, we looked at that in the reverse order. If I said take the derivative of f of x with respect to x, and then take the antiderivative of all of that, what do you think that's going to give us?
f of x.
f of x, yeah. The antiderivative of the derivative, they're inverses of each other. I mean, more technically, we know that when if we perform a derivative here, we get some function, and then we take the antiderivative of that function, we would get this, a more general antiderivative is f of x plus c. But the idea is that if I apply one and then the other, I'm back to where I started. With the exception of the antiderivative and the plus c thing, again, we can sort of address that later. So if we're looking at something and we're like, hey, I don't know how to find the antiderivative of that, when we think in reverse, we don't quite get there. But if we think about derivatives first and then antiderivatives, we can get a derivative formula. It may not be the one we're after, but it can help us kind of piece together how these antiderivatives are determined. So like a specific example would be, for example, if I start off with the derivative, we'll just say something simple here. If I start off by saying the derivative of sine x is cosine x, we start off with a known derivative formula, I guess. But then we introduce an antiderivative. Say, I'm going to take the antiderivative with respect to x on both sides. So it's just like taking the square root of both sides, or squaring both sides. On the left, what do we get? What's the antiderivative of the derivative of sine? Just sine. Okay, so the left-hand side is just sine equals to the antiderivative of cosine x dx. So then, you know, plus c, whatever, but you have an antiderivative formula for cosine now, because you knew the derivative of sine. All right, that's kind of how we can, maybe not necessarily like, so if it's not terribly helpful if I don't know the antiderivative of cosine, like I can't reverse engineer it in that respect. But if I can remember my derivatives, all of my derivatives will give me another formula for an antiderivative, is the whole point. Does that, what we've done there, does that actually make sense? Does anyone have any questions or comments on that? So it's like you know a derivative, then just take the antiderivative of both sides. If I know that the derivative of e to the 3x is 3e to the 3x, which again, we should know these derivatives. So I know that derivative is that, then I can also get an antiderivative formula by taking the antiderivative of both sides and getting on the left e to the 3x equals the antiderivative of 3e to the 3x. Yeah? That makes sense? But I can also divide then both sides by this 3 here and say e to the 3x over 3 is the antiderivative of e to the 3x. Just divide both sides by 3. Is that weird?
Yeah.
A little bit, yeah. But now we know, like, the antiderivative of e to the 3x is e to the 3x over 3. Whereas the derivative of e to the 3x was e to the 3x times 3. So we can look at it that way too. If the derivative involves multiplication by this thing's derivative, the chain rule, then the antiderivative will involve division because they're reverse processes of each other. So then we could like maybe even say, all right, well, maybe look at something more generic. What's the, well, we'll start off this way. If I know the derivative of, just make it generic, e to the a times x power. If I know that derivative is a times e to the ax, then I take the antiderivative of both sides. The antiderivative of the derivative here just leaves us with e to the ax. It's the integral, or sorry, the antiderivative of a times e to the ax dx. Yeah. And then I divide both sides by a. I have the antiderivative of e to the a times x power is e to the ax divided by a. So I'll give you a handout of antiderivative formulas here in a minute, and that's kind of where they're going with a lot of those. Does anyone have any questions? I mean, I think this process serves its purpose up to a point, but we have so many functions that I would honestly just remember their antiderivatives, just like you had to remember derivatives. But I think this is a worthwhile process to look at. When you see the formulas for all the antiderivatives that are given, you're not overwhelmed when you kind of see where they come from. Already mentioned that. Sorry, my notes are out of order. But so we do get one rule for finding antiderivatives, and we'll just leave that. It's worth mentioning again. We get one rule for antiderivatives in this section. If we just look at how we take the derivative of powers, we said, all right, well, the power comes out front, multiply by the power, and then we subtract 1 from the power. If we're talking about the antiderivative being the reverse operation or the inverse operation of derivatives, then we just need to reverse that process, right? Instead of multiplying by the power and then subtracting 1, we would add 1 to the power. Then divide by whatever that result is, 1 plus the power. Is that reasonable as reversing the derivative for a power? Derivative multiply, then subtract 1 from the power. The antiderivative is just the complete opposite of that. You first add 1 to the power, then divide by the result.
You're dividing the coefficient by 1 plus power.
Yeah, you're dividing everything by, just like we multiplied everything here by 3, we would divide everything in the antiderivative by 3. So I don't see that here. Let me add that in. Yeah, so when you see the power rule for indefinite integrals, this is just antiderivative here. It says to find the antiderivative of x to any power, you first add 1 to the power and then divide by the result, 1 plus p. It says where p is not -1, p is a real number and c is our constant. So what happens if p is -1?
You add 1, you get a power of 0.
Right. So if p is -1, then it says What's the antiderivative of x to the negative 1 dx? So that's, you can't divide by 0. So how do you actually take the antiderivative of x to the negative 1 power? Yeah, it's just 1 over x. What's the antiderivative of 1 over x?
Natural log.
Yeah, so when p is negative 1, this is just the antiderivative is the natural log. For any other power, it works. Like, so that means all of our radicals, right? When we took the derivative of radicals, we considered those powers instead. Same thing, if you have to integrate, or if you have to find the antiderivative of x, x squared, the cube root of x squared, you would rewrite that as a power and just apply this power rule to it. Okay, so what's the antiderivative of x to the 5th? What function do we take the derivative of to get x to the 5th?
X to the 6 divided by 5.
X to the 6 divided by
6.
6, right? The power rule says we take the original power and add 1 and divide by the same result. So we can check that really quickly. What's the derivative of x to the 6 over 6? It's 6x to the 5th over 6, which is x to the 5th. Okay, we've got a radical here. We're going to rewrite that as x to the 1/2 power. And then apply the power rule. Add 1. To find the antiderivative, then, we add 1 to the power and divide by the same result. So x to the 1/2 plus 1 power divided by 1/2 plus 1. So that's x to the 3/2 divided by 3/2 plus c. Yeah. Or 2/3 times x to the 3/2.
So here, whatever time we're doing it, we're just calling the bottom of it the constant. So like on the first one, it'd be 1/6 times x to the 6, and that's how you do it?
Yeah.
Okay.
Yeah. Do y'all have any questions on this? I know it may seem like a really drastic shift of gears at this point, but again, this is directly related to derivatives, which is why it still shows up in Chapter 4. Chapter 4 is what can derivatives tell us? So this is over here. What's the antiderivative of 12 with respect to x?
12x.
Yeah, so what function do we take the derivative of to get 12? We're thinking about that as a power rule, but it's just 12 times x to the 0. So we add 1 to the power, divide by the same result. So just 12x plus c. So what's the derivative of, or sorry, antiderivative of any real number? Yeah. Yeah, plus c. The antiderivative of any constant is that constant times x plus c. Do you have any questions? So there's a couple of rules that we have similar to those of the derivative and those of the limits. If you've got a constant multiple times a function, it's not acting, the antiderivative is not acting on that constant times that function. So the constant can be pulled out of the antiderivative process and multiplied in later. With the sum or difference, the difference is implied here, just addition of the opposite. We can go ahead and put that in. The antiderivative of a sum or difference of functions is the sum or difference of antiderivatives. So this kind of gives us, with our power rule, it just builds up into how do we find the antiderivative of a polynomial, like 5x to the fourth minus 3x squared plus x minus 5. So then we can just rewrite this. And maybe in practice you don't write all of this out, you just kind of do it individually. But we'll write this out as that theorem 417 says to do. And then we can look at those individually as far as antiderivatives go. So what would be the antiderivative of 5x to the fourth be? X to the fifth. And technically if we break it up this way, we would get a constant here. So let's call that constant 1 minus the antiderivative of 3x squared. What would that be? X cubed, yeah, minus x cubed plus another constant plus the antiderivative of x. What would that be? X squared over 2, right? We add 1 to the power, divide by the same result. You get another constant there, minus, what's the antiderivative of 5 with respect to x? 5x. And then another constant. But when we take this constant minus this constant plus this constant plus this constant, isn't that just another constant?
Yes.
So again, at the end, you're just going to have a plus c, because all of those constants would combine into a single constant. So really, we can just say it's x to the fifth minus x cubed plus x squared over 2 minus 5x plus c. Any questions? Yeah.
Question.
Sure.
Previous, it was the antiderivative of the e to the ax. So you took the antiderivative of that, which was the e to the ax.
The derivative. We took the derivative of e to the ax.
Yes.
Yeah, which was ae to the
But the
ax.
antiderivative is the e to the ax.
Yes.
But then in the next step, are you taking the antiderivative again?
This step here or this step here?
The second.
This step?
Yeah.
No, we said that we took the antiderivative of the derivative equation.
Mm-hmm.
And so the antiderivative of the derivative it just canceled out, and we're just left with that. And we just left this as it is.
And
And
then
that
what's the
second
next
step. The third step is when we divide through by a.
Is there a reason why you do that?
So we divide by a. Yeah, because we're usually looking at the antiderivative of a function. It's a more general form.
But that is the antiderivative of e to the ax.
Yes, correct. The antiderivative of e to the ax is e to the ax over a. Yeah. And so that's on this formula sheet up here. As you leave, just take one of these. It's also on D2L, but you don't have to print it out. Just grab one on your way out. I'll see y'all Thursday.